So, let us now consider the next case which is the particle in a one dimensional box, but instead of the potential being infinitely large outside this box, we will now lower the potential to a finite value. Okay. So, it is exactly the same kind of a diagram or kind of a potential profile, but the only big difference is that these potentials that you see here were initially infinite, I have now made it finite and it has got a value of V naught, okay, and this is no longer infinity. And you still have the particle, although I have drawn it as a discrete particle, we should remember that it is actually a wave function. And for the sake of simplicity, let us actually define this box to be at minus L by 2 and L by 2. Okay. So, that everything that happens is we will watch out for symmetry across x equal to 0. Okay. So, that is our definition. So, how do we write Schrodinger's equation? Now, inside the box, we firstly let's write Schrodinger's equation in a very general sense. So, you have minus h power square by 2m dou square psi by dou x square plus v psi is equal to E psi. So, this is Schrodinger's equation, and we always wanted to identify what this potential was. And just like in our previous case, inside the box we can define the reference potential to be 0. Okay. And once again let me correct these axes because that sort of is consistent with what I have written later. And inside the box we find that Schrodinger's equation is simply this, because my potential term is 0, because the potential is 0 inside this box. Now, outside the box, in the previous case when we considered an infinitely high potential barrier, we had assumed that the wave function does not exist, right, and we went ahead to only solve for the wave function inside the box. But now we can write Schrodinger's equation outside the box, and using the same idea here, you will be able to write Schrodinger's equation outside the box, and instead of the potential being arbitrary V, it is actually V naught, because that is the way we have defined our potential. Right. So, outside the box the potentials the Schrodinger's equation would take a form that looked like this. So, you have your kinetic energy, you have your potential energy that is equal to the total energy, and inside the box we have Schrodinger's equation taking a form like this. And we will define the coordinate system to be x equal to minus L by 2, x equal to plus L by 2 on the right side. Therefore, the box still got a width of L, and from x equal to L by 2 all the way till infinite you have this Schrodinger's equation. From x equal to minus L by 2 all the way down till minus infinite you have this Schrodinger's equation, and inside the box, that is from for the region of minus L by 2 less than equal to x less than equal to plus L by 2, you have this Schrodinger's equation. So, I will call this as region 1, call this as region 2, and call this as region 3. So, you have 3 different regions and you have written Schrodinger's equation for each of these regions. So, just to summarize, these are the 3 wave functions. We have psi 1 for region 1, and if I just draw the box here again, this is psi 1, and then we have psi 2 for region 2, and you have psi 3 for region 3. Now, the first point is that let us assume that E is less than V naught. Okay. Now, this seems to be a very difficult assumption to take in if you observe this carefully. So, what are we saying here? By saying that E is less than V naught, what we are saying is that yes, the particle does exist somewhere and it has got a total energy E, and that total energy E is less than the potential height in region 3. And we have still gone on to write Schrodinger's equation in the manner shown here. Okay. So, what we are saying is this is the kinetic energy, this is the potential energy, and the sum of the kinetic energy and potential energy is equal to the total energy, and that total energy term is less than V naught, which means the total energy is less than the potential energy. Okay. Now, that sounds a bit odd, okay, but it is one of the main features of quantum mechanics. So, if E is less than V naught, and if I have to describe a wave function here in this region, regions 1 and 3, then what I am trying to tell you is that the kinetic energy has got a negative value. Okay, that's the implication of it. I mean that's what classical mechanics would tell you. Okay. In classical mechanics, if E was less than V naught, there is no way the particle can have an existence outside region 2. Okay. But what we are seeing here is that we are able to write the Schrodinger's equation. There is nothing to stop us from writing Schrodinger's equation even outside the box. Okay. So, let us see where this leads us. Now, firstly let us get some definitions clear. Okay. So, we have this to be our Schrodinger's equation. I am just going to take the V naught term, pull it over to the right side, okay, and get rid of the negative sign here, and I am going to write the same equation in this manner. So, I have taken h bar square down here, 2m has gone up there, and this is V naught minus E, and therefore, the negative sign of this term has disappeared. Okay. And we will just call this entire term component here, to be equal to alpha square. So, since my E is less than V naught, alpha square or alpha is greater than 0, sorry. And similarly for the region in region 2, we have Schrodinger's equation to be the kinetic energy is equal to the total energy. Okay. And I can rewrite this as dou square psi 2 by dou x square is equal to 2m E by h bar square. And we will define this term here as minus k square. Okay. Now, this is a situation that is similar to what we have done before. The only thing is I am trying to bring in consistency between the way we represent these equations. Okay. So, we have minus k square where k again is greater than 0. So, my k will be square root of 2m E by h bar square. So, that is my k, and in this case my alpha is square root of 2m V naught minus E by h bar square. Similarly, for region 3, we write Schrodinger's equation in a manner which is quite similar to region 1. Okay. So, once again we define the alpha is the same. So, we have Schrodinger's equation in region 3 to be this. So, that is region 1, that is region 2, and this is region 3. Now, the big difference between region 1 and region 2 is that here alpha is positive and this entire term is positive, but here since k is also positive, there is a negative sign here, and therefore, this entire term is negative. Okay. So, that is the big difference, and once again in region 3 you have a positive term on the right hand side. So, since I have Schrodinger's equation in that particular manner, I can write an expected solution for the wave function. So, as I mentioned, in this region the right hand side term is positive, okay, and we need to guess a solution for say psi 1. So, that when you take the second derivative you end up with a form that has got psi 1 in it, and it has also got a positive term. Okay. And that solution could be of this form. Okay. It will have, if you have exponentials of a real number, then you will end up with a possible solution for that. Similarly, in region 3 you have a similar description where you have exponentials of a real term. But in region 2 we already saw that you could describe things as sines and cosines. When we solved Schrodinger's equation for the equivalence of region 2 in the infinite potential well case, we saw the sines and cosines appearing in the equation. And equivalently, you have, if you write it in terms of exponents, you are going to have exponents of complex quantities that are appearing in region 2. So, and by Euler's notation, you have this being equivalent to your sines and cosines. So, these are the three general solutions that are possible. Okay. So, psi 1 is expected to look like that, psi 2 is expected to look like that, and psi 3 is expected to look like this. Now, how many terms do we need to identify? We need to identify A1, B1, A2, B2, A3 and B3. Okay. And what are the properties that we have? We have that firstly psi has to be a solution of Schrodinger's equation. That is all satisfied by defining psi in this particular manner. That we must have psi to be continuous. You must have d psi by dx also to be continuous, and you must have psi not blow up. It should be normalizable, it should not blow up anywhere. And basically equivalent to this condition is also the other side of it, which is that the particle must exist somewhere, and therefore in this space from minus infinite to infinite, the particle must exist somewhere. Therefore, the probability of finding the particle in some region there is 1. Okay. So, we have all these terms to play with. Now, let us just go through the process of elimination and trying to bring out some useful results here. Okay. So, first let us take the region 1. Okay. So, let me redraw the box here. So, that was my region 1, that is region 2, and that is region 3. And for reasons mentioned before, this is the general solution for the wave function in region 1. This is the solution for the wave function in region 3, and for region 2 you have sines and cosines. Okay. Now, let us take region 1 first. Okay. So, let us not worry about region 2 and 3, let us just take region 1, which is this region. Now, let us imagine, since this is the general solution, let us start seeing what happens to the solution if I start moving towards minus infinity. I start walking in this direction and go from x equal to minus L by 2 to minus infinity. Okay. At x equal to minus infinity, so as we start moving in the direction, what happens to this term? Now, alpha is positive. So, as x starts getting more and more negative, this term starts dying out. Okay. What happens to the second term? Since alpha is positive and x is negative, this negative sign disappears, it becomes a positive value here. So, you have e to the power a positive quantity, and that positive number starts increasing as I head towards x equal to minus infinite. So, this term starts increasing as we head towards minus infinity. Now, we already mentioned that the wave, you can't have any of these components blowing up, which means you can't have them head towards infinite. Okay. And since this is doing exactly that in region 3, in region 1, as I move towards minus infinite, this term can't exist. Okay. You can't allow this. This might be a general solution, but this term violates this very basic principle that you can't have the wave function blow up. Okay. Therefore, the B1 term has to be 0. Okay. And if B1 is 0, I can just write my solution to be just this, psi 1 is equal to A1 e to the power alpha x. So, that just by a process of simple but just using simple arguments, you have eliminated one of the coefficients. You do not have to identify that. Okay. Now, what about region 3? Now, you can make the same argument here, but the only thing is that region 3 exists from plus L by 2 all the way till infinite. So, now if you start moving towards plus infinite, Okay, you can't head towards minus infinite because that's not region 3. Okay, so psi 3 isn't valid for if you're heading towards minus infinite. So as you head towards plus infinite, what happens to these terms? Alpha is positive and you're heading towards plus infinite, therefore this term starts blowing up. Okay. Now here you have a negative sign and alpha is positive and you're increasing x from L by 2 to infinite, therefore this term starts dying out. Okay. And since once again, since you cannot allow the wave function to blow up, this component cannot exist. You cannot allow that. Okay. Therefore in region 3 the wave function must take a nature that looks like this. Now in region 2 you could have sines or you could have cosines. Now in the case of an infinite potential well, if you remember the infinite potential well, okay, where we had a solution, a general solution of I think we used A and B there, A sine kx and B cos kx. When we had this general solution, at the point of x equal to 0, when we apply the continuity of the wave function at x equal to 0, sine of kx at x equal to 0 was not non-existent, but the cosine term became 1 and therefore the term b had to disappear because the wave function had taken a value of 0 outside the box. So that was, if you just recollect the infinite potential well case, that's what happened. So the cosine never existed in that case, but such a boundary condition need not happen now because psi need not be equal to 0. So you could have the cosine term surviving because there is no condition for the wave function to be 0 when x is 0, for example. Okay, there is no enforcing condition there. So you could have both these cases. So if that's the situation and we only look at symmetric solutions of the wave function, so we will look at solutions that are sort of symmetric around this midpoint. Okay. So you could have psi taking a sinusoidal expression or it could have a cosinusoidal expression. So this would mean that the wave function is even. Okay, so it's got the same sign on both sides of the symmetry, and this would mean that the wave function is odd. The sign changes as you cross the symmetry. Okay, so we can look at both these solutions. So you have psi 1, you have psi 3 and you have psi 2, which could be either this or that for the purpose of symmetry. So let us go through an example of having these three cases. So that is my psi 1, that is my psi 3, and let us say we are looking at even wave functions in region 2, and let us say that is my wave function in region 2. So firstly, how do we identify all these terms? Okay, now the first thing we do is, okay, let us say the wave function is continuous. Okay, so the wave function, you have the box here, this was x equal to minus L by 2, that was x equal to plus L by 2, and that is x equal to 0. Now this is region 2, that is region 3, and that is region 1. Now if you look at this boundary here, since the wave function has to be continuous, psi of psi 2 at this point must be equal to psi 3 at this point. Okay, so psi 2 at x equal to L by 2 must be equal to psi 3 at x equal to L by 2. Okay. Now what is psi 2 at x equal to L by 2? You have C2 cosine k L by 2, that is my psi 2. Okay, so this is a typo, please pardon me, there should be a plus here. So that is psi 2. And what is psi 3? Psi 3 is given by b3 e to the power minus alpha x. Okay, so we saw that only the decaying term is allowed here, so it was b3 e to the power minus alpha x. That is my psi 3, and once again there is a typo here, there should be a minus sign. and therefore at x equal to L by 2 psi 3 takes a value of L by 2 e to the power minus alpha L by 2. So, this is the first condition, which is simply the continuity at L by 2. Now, since we are looking at symmetric cases, there is you are not going to learn too much by applying the same continuity at minus L by 2. Okay, so that is not going to give you too much of new information, but we have whatever solution holds here, you could just directly apply the solution on the other side, just taking into consideration the direction in which we move. So, this is the first condition. Okay. Now, what is the second condition? So, we have these three solutions. We have the second condition, this is the continuity constraint, but this first derivative of the wave function must also be continuous, right. So, if I have x equal to L by 2 here, I must also have not only psi being continuous, but I also need d psi by dx to be continuous. Now, since the wave function has got a form psi 2 in this region and it has got psi 3 here, I need d psi 2 by dx at x equal to L by 2 must be equal to d psi 3 by dx at x equal to L by 2. So, the first derivative of the cosine is going to be minus, it is going to yield minus C2 k by 2 sine of k L by 2, and this is going to yield this term, alright. So, you now have this condition and you have this condition, and now you can go ahead and apply the condition that the probability of finding the particle somewhere in all three regions has to be 1. Okay. But let us not head there, because let us just investigate what needs to be investigated at this point, because those details do not really serve our purpose too much. So, what we are going to do is just examine these two terms. Now, you see this, you have a sinusoid, you have a cosinusoid, you have C2 C2 and you have B3 B3, and you have the same kind of an exponential term. So, suppose I were to label this equation as equation 2 and this is equation 1. What I would like to do is divide equation 2 by equation 1. Okay. So, you will have the negative signs have already gone here, the 2 will disappear, and if you were to divide this term by that term, then you will end up with the condition that the tangent of KL by 2 is equal to alpha by k. Now, k is an important parameter for us because you have k defining the wave number in some sense. Okay. Now, if you ask yourself the question, in the case of an infinite potential well, what were the values k took? So, in that case you had to meet the condition that KL was equal to 0, and therefore, k could take integer values of pi by L. Now, in this particular case, for a finite potential well, k can only take those values where this equation is satisfied. Okay. So, if you were to plot both these functions, okay, let us plot alpha by k as a how does alpha by k vary with k? Okay, it would probably vary in this manner, and then you plot how tangent of KL by 2 varies with k. Okay, you will get another plot, and if you were to take the points at which these two functions meet, those are the values of k those are the solutions of these particular equations, and only those values of k are allowed. So, no other values of k are allowed, and then you could use this k to define your energy. So, that is the first point. Now, the second point is, if you consider the odd symmetry case, that is psi 2 being C2 sine of k of kx, you will end up with a condition that the cotangent of KL by 2 must be equal to minus alpha by k. So, once again k can take only those values that are permitted by the solution to this equation. Okay. So, as I mentioned, it really does not serve our purpose too much to spend a lot of time calculating the exact values of A1, C2 and B3. But what's useful to note is that the solutions will have, the wave functions will sort of look like this. So I've sort of sketched the wave functions here. So in the case of an infinite potential well, the wave function existed only inside the box. So we found solutions like the wave functions to be like this. Now in the case of a finite potential barrier, we have already seen that psi 1 and psi 3 can have an exponential solution. So if you look at psi 3, it varies as e to the power minus alpha x, with alpha being a positive number. So which means that the wave function has got a decay in space in the x direction. Now mathematically that looks fine, okay, it's not, doesn't seem to be very difficult because the exponential came out from the differential equation. But just imagine what it is implying. You have a finite potential barrier, okay, and you've got the total energy of the particle to be less than the potential energy of the barrier, okay. So according to classical mechanics, the particle can never climb over the barrier. But what quantum mechanics is telling you is that by solving Schrodinger's equation, we are finding that the wave function exists outside this well and it exists by decaying exponentially with the distance, okay. So the wave function exists and it decays exponentially with the distance. So that's a very big message. What quantum mechanics is telling you is even though E is less than the height of the barrier, the particle can exist in that region, okay. So if you imagine, if you remember, psi is indicative of, psi square is indicative of the probability density function to find or finding the particle in any given region. So psi square dx is the probability of finding the particle between x and x plus dx. The probability of finding the particle between x equal to L by 2 and infinite is now given by psi 3 square dx L by 2 to infinite, and what quantum mechanics is telling you is that this probability is not 0 even though the total energy of the particle is less than V naught, okay. Now that is a very amazing result if you think about it, okay, but it is so naturally seen if you simply solve Schrodinger's equation, okay. But this result is important and it is in fact used on a day to day basis. It is not that it is an interesting exotic result that has got no implication. Now if the particle, for example, if the particle could not exist in this region, many of the devices, since we are talking about a semiconductor device course, many of the devices and instruments that you use probably would not work. For example, the injection of carriers at the source drain, okay. The source drain regions are doped so as to encourage the injection of carriers through a mechanism like this in a MOSFET, okay. If you have heard of something called as a scanning tunneling microscope, that too works on the principle of trying to measure the electrons that have escaped the well and are found inside a barrier, okay. So this mechanism of getting the particles to go through the barrier, if you may, if you imagine the wave function is going through the barrier, okay, despite the fact that E is less than V naught. This mechanism is something called as tunneling, okay. It is a technical term, but if anyone sees the word tunneling, this is what they are talking about, okay. So this is what they need to think about. So that is a very important message of quantum mechanics. So if you have to summarize two important things we have learned so far, the first is that particles also have a wave and that wavelength is given by the de Broglie's equation, lambda is equal to h by p, and the second is the fact that the wave function can exist outside a barrier even though the total energy is less than V naught. So these are two important essential points. Now before we wrap up quantum mechanics, the topic, let us just quickly go through another example, okay, of using Schrodinger's equation, and this is an example of something called as a harmonic oscillator. So we want to see what's the nature of the wave function here. Okay. So let's write down Schrodinger's equation for in a very general sense. So that's the kinetic energy, that's the potential energy, and that's total energy. And since we are talking about an oscillator, I think the easiest way to imagine one is to imagine the equations for a spring. Okay. So if you remember, the spring, if you apply a certain force to a spring, then it's got a certain spring constant, okay, which I've used the symbol F for it, but in textbooks you might probably see the symbol K. It is just that we are using K too many times. So let's say F is the spring constant, then the force will be given by the spring constant times the displacement. Okay. So you can imagine a little spring, a quantum spring if you may, okay, that we are trying to describe here. Now that's the spring constant, and the potential energy stored in a spring is F x square by 2. Okay, that's half the spring constant into x square, where x is the displacement. And if I were to let the spring go and oscillate, it would have a natural oscillation frequency of omega, which is equal to the spring constant divided by the mass per unit length. The mass to the power half. Okay. And the potential energy term would be can be rewritten by writing F in terms of omega and m as m omega square x square by 2. So that's my potential energy term. Okay, so with this introduction, let's just use this term for the potential term in my harmonic oscillator. Okay, so that's Schrodinger's equation, and that is V. E is a constant, and that's the kinetic energy. So that would allow us to write Schrodinger's equation in this particular manner. Now how do we solve this? Okay. Now this equation seems to be a little bit more complicated than the ones you encountered in the case of a particle in a box. Okay. So how do we go about solving this? So we make a good guess. Okay, that's usually the case for many situations. We make a good guess, and our guess is psi is equal to e to the power minus alpha x square by 2. And why is this going to be our guess? If you think about it, the right hand side here has got a e that's a constant. Okay, that's a constant here. There is no dependence on x. There is no x at all on the right hand side. But on the left hand side, you have a dependence on x here, and you have a dependence on x in this term. So somewhere by solving all this out, that x dependence must cancel off. Okay. And what is the x dependence? It's very obvious that you have a factor that's multiplied by x square sitting here. So I cannot allow that to exist after I've taken the derivative and cancelled all the terms. This term cannot exist. Okay, because otherwise if it did exist, then I do not see an x square on this side, and therefore it's not a correct solution. So this term cannot exist. So what is the psi that I could use so that if I take a second derivative, it would end up with an x square, a term which has an x square in it, some factor beta into x square, such that that beta would be equal to m omega square by 2, and therefore cancel off with the potential term here. Okay, so the idea is to eliminate x square from this picture, and this seems to be a good guess for that, because what is d psi by dx? D psi by dx is minus alpha by 2 e to the power minus alpha x square by 2, and then you take the derivative of the x square term, which is 2x. So this is nothing but minus alpha x e to the power minus alpha x square by 2. What is d square psi by dx square? D square psi by dx square is minus, so you first take the differential of the x, so it's minus alpha e to the power minus alpha x square by 2 minus alpha x, and you again differentiate this term once more, and you will end up with minus alpha by 2 e to the power minus alpha x square by 2 into 2x. Okay. So this is going to be a minus alpha, so let's call this psi because that's what our wave function is. So it will be minus, and you have you have a minus and minus here that would end up being a plus alpha square. These two terms would cancel off x square psi. Okay. So you see that you have a constant times psi and you have something which is got an x square component in it, and going by our argument this component should cancel off that component there. Okay. So for me to have all this work out, we need alpha square x square psi into minus h bar square by 2m. Okay. So minus h square by 2m, okay, must be equal to this particular term, okay, must be equal to your m omega square by 2. So we don't need to retain the negative because it's going to that's the opposite sign for you to cancel. So the magnitudes of these two needs to be the same. So this m omega square x square by 2. So this implies that my alpha, okay, so this also got a psi here, so pardon me, okay. So this implies that my alpha is going to be m omega by h bar. So that is my alpha, okay. So here is all this written out quite neatly. So I need these two terms to be equal, and therefore my alpha has to be m omega by h bar. If alpha is equal to m omega by h bar, then I can now use this particular value of alpha to calculate what my E is. Okay. Now these two terms have cancelled off. So what's left is, on the left hand side, is minus h square by 2m into minus alpha psi is equal to E psi. Implies my energy is minus h bar square by 2m into minus alpha, which is h bar square by 2m into alpha, and that using the value of alpha you have h bar square by 2m into m omega by h bar is my total energy, and which is going to be equivalent to your h bar omega by 2. Now what we have done here is we have only looked at the so called ground state energy. So it is not a very general solution to Schrödinger's equation. We just assumed one particular solution. It could have had constant coefficients, for example, but that solution could be represented in a much more general way, and we haven't done that here. But through these simple arguments we saw the nature of the solution, which is that the wave function must have a exponential of minus alpha x square by 2 component. Okay, so that's the nature of the wave function, and we found that the energy scales as h bar omega by 2. Okay, now this is a very useful relation which we will come back to later on.